let's just recap on what we know about Taylor series and Taylor polynomials and Maclaurin series and Maclaurin polynomials with a familiar function f of x equals cosine x. So here I've plotted cosine x, and you're probably familiar with the graph. It's just an infinite wave from minus infinity to infinity. And this function has a Maclaurin series, that's the Taylor series around 0. It has infinitely many derivatives at 0, and we've already calculated that Maclaurin series. We took all of these derivatives at 0, and we got cosine is the 0th derivative minus sine minus cosine. We saw that these derivatives repeated every 4 derivatives. So to get the Maclaurin series, or the Taylor series at 0, we evaluated all of these derivatives at 0 and got a string of numbers. And of course f of 0 is 1, f prime of 0 is 0, f double prime of 0 is minus 1, and we get this repeating pattern of 1s and 0s and minus 1s. Then we constructed the Maclaurin series by calculating the sum as n ran from 0 to infinity of the nth derivative evaluated at 0 divided by n factorial times x to the n. And we saw, because of all of these zeros, whatever the x was, that this was an alternating series and only the even powers remained. Now the third Taylor polynomial is going to be the sum of the first few terms of that series up as far as the x cubed term. But of course there's no actual x cubed term in the Maclaurin series for cosine of x, so this sum stops at minus x squared over 2. So the third Maclaurin polynomial, or the third Taylor polynomial for cosine of x at 0, is 1 minus x squared over 2. And now one of the great uses for Taylor polynomials is that they give us polynomial approximations to functions. This third Taylor polynomial is obviously a quadratic, so its limit as x approaches minus and plus infinity is going to be minus infinity. So it's certainly not going to approximate cosine of x near plus and minus infinity. But near 0, we see that this is a very good approximation to the graph of cosine of x. In fact, I've drawn both of them here on this plot. You see the graph of cosine of x in blue and the graph of the third Taylor polynomial in red here. And we see that this polynomial gives us a very, very good approximation to cosine of x between minus 1 and 1. Now, if I increase the number of terms in the Taylor polynomial, if I take the fifth Taylor polynomial, then that should end at x to the 5. But of course the coefficient of x to the 5 for the Maclaurin series for cosine is 0, so the fifth Taylor polynomial for cosine at 0 is 1 minus x squared over 2 plus x to the 4 over 24. And the seventh Taylor polynomial adds another term to that. It adds minus x to the 6 over 720. And as I increase the degree of the Taylor polynomial here, the approximation to cosine of x gets better nearer 0, and of course the interval where the nth Taylor polynomial is a good approximation to cosine widens as the n increases. Well, here I've created an animation where it shows the graph of the nth Taylor polynomial, where the value of n is given on this slider here. And it shows the graph of the nth Taylor polynomial in red, and it also shows the graph of cosine. So we can just let that animation run, and you see that as the degree of the Taylor polynomial increases from 0 to 80, this becomes a very good approximation. And in fact, on the interval from minus 10 to 10, when we get to about the 30th Taylor polynomial, then its graph is almost identical to that of cosine of x between minus 10 and 10. And in this animation, I've widened the interval on the graph of cosine extending from minus 35 to 35. And now you see, as I increase the degree of the Taylor polynomial, its graph gets closer and closer to the graph of cosine along this interval. So the approximation gets better and better in this interval between minus 35 and 35. So when I get to the 80th Taylor polynomial, it's a pretty good approximation to cosine of x between minus 30 and 30. Now, there's no reason why I should be interested in the values of cosine around 0. I might be interested in the values of cosine near pi over 2. And in which case, if I'm approximating the function cosine of x, I would use the terms of the Taylor series at a equals pi over 2. And of course, I would use the nth degree Taylor polynomials at a equals pi over 2. So here I'm generating the 10th Taylor polynomial at pi over 2 for cosine of x. And Mathematica does this in an instant. I can generate the 50th degree Taylor polynomial for cosine of x around pi over 2. And this is a very large polynomial, but nevertheless it is a polynomial and it's pretty easy to deal with. However, the 10th degree Taylor polynomial is a little nicer, so I'm going to work with that for now. Again, we've created an animation here which graphs both cosine of x and the nth Taylor polynomial for cosine of x at a equals pi over 2, where the n increases from 0 to 80 once again. And notice that these polynomials become a good approximation to cosine of x on intervals that are symmetric around pi over 2. So the best approximation is given at pi over 2, where the value of the polynomial equals the value of the function, its cosine of pi over 2. And as we take larger and larger Taylor polynomials of the function at that point, we get a better approximation to our function on a wider interval around pi over 2. And you can see this happening on the graph when I run the animation. It starts out being a good approximation centered at pi over 2, and then gradually the interval on which it's a good approximation widens as the degree of the polynomial increases.